Well, I'm going to talk to you about vectors. You don't need to know what a vector is initially, but it has something to do with motion. And so let me start off by making something move. This is already cocked. It says a Superman space gun. And let it roll. Let's see what happens. All right. May I have it? Thank you. The motion actually was rather complex. And we will discuss motion by discussing the very simple things first. But now let me show you how vectors come into the picture. I still haven't told you what a vector is, but this is what a vector looks like. At least this is how we imagine it. This is a model of a straight line, an arrow head. I will call this the head, and I will call this the foot. Now, suppose I want to discuss the motion of this object. I will not try to discuss the rotary motion, but suppose I just want to discuss the motion of the center of gravity. And here we are. Now this thing moves around, like so, let's say. At every instant, the rubber vector, I'll call it that, has direction and magnitude. Magnitude meaning size, direction having something to do with angles. You see, I could erect X, Y, and Z axes and measure angles. Now, we're not going to do much computing during this picture, but direction and magnitude are important. If I knew the direction and magnitude at every instant of the trajectory, I would have solved the problem of motion. So you see that vectors are going to have something to do with motion. I can do something else without telling you what a vector is. I can tell you when they're equal and when they're not equal, still without defining what a vector is, just by demonstrating. Here I have two vectors. I call that one the green one and the red one if you like. These are unequal vectors. Their magnitudes may be alike, but their directions are different. Now I will also call these unequal vectors. Their directions are alike, but their magnitudes are different. And so I have all sorts of combinations. These are all unequal vectors, you see. Now, these vectors, if they have the same magnitude and the same direction, will be called equal vectors. So this equals this equals that. Now they're different. This is a different one, but this equals this. And so under the circumstances where the direction and the magnitudes are alike, we will call them equal vectors. Now obviously, I don't need three-dimensional vectors to illustrate this, so let me go to the blackboard and put down a summary of what I've just said. If I draw two parallel lines of equal length and I put arrowheads on them, if the sizes are alike, that means magnitude. If the directions are alike, and notice that they don't have to be tied to a common point, they can simply be displaced but parallel, then I will say that this vector equals this vector. This is the kind of notation we will use, a letter with a little arrow over it. This one I will call B. And so I have two vectors, A and B, and what I am illustrating here can be stated mathematically, A equals B. See, it's the beginning of an algebra. I'm using algebraic symbols. So we're inventing an algebra of vectors. In any algebra, there are several other operations that you have to worry about. Let's consider, for example, the operation of addition. Now, we'll do this as if we were learning a new game. You know, when you learn a game, someone tells you the rules, you don't argue with them, you simply accept them because someone has told you that if you learn it, you'll have some fun. So in that spirit, first I will just toss the rules at you, and then later on and see what the motivation is. So I'll say, here's a rule. If I want to add two vectors, let me call this one C, and let me call this one D. The rule is that you tie them end to end. You put the foot of the second one where the head of the first one is, and connect them so that you preserve direction and magnitude. Now the vector that starts at the very first foot and ends at the very last head, like that, is called the resultant. And now I will use the symbol plus and say the following. R vector equals C plus D. My algebra is increasing. I'm using now the symbol equals and the symbol plus. Notice, however, that this is not ordinary algebra, because C and D are not numbers. Nevertheless, I've written down what looks like an algebraic equation. So I am inventing an algebra in which the elements are things called vectors. They're not just ordinary numbers. From this drawing, I can get another interesting fact, namely that the order in which I make these operations doesn't make any difference in the final result. Look, suppose I took D first and drew it there. Then tagged onto that C, like that. Obviously, D plus C gives me the same resultant as C plus D, and therefore I will put here D plus C. That's another interesting thing about certain algebras. We say they obey the law of commutativity. The operation is commutative. C plus D equals D plus C. It means that these things are interchangeable. So we've learned quite a bit about our algebra, what equals means, what addition means, and that it obeys the law of commutation. Very well. Now I'll go back to my three-dimensional vector model because I can illustrate how easy it is to visualize the addition of vectors even in 3 dimensions. Let me motivate it by considering this as if it were a helicopter. At least it looks like a certain part of a helicopter. Suppose a helicopter taxied along the field and went northward for 100 yards and then went west for 100 yards. I would illustrate that by 2 vectors like this. This plus this, you see. The resultant would be the vector that goes from the initial starting point to the very last terminal point over here. I'm not going to connect it there because I want to go immediately to the 3-dimensional case. And so I'm about to ask, you see, what would happen if the helicopter went first 100 yards north, 100 yards west, and then 100 yards straight up? The question I'm about to ask is this. What single displacement, I'm using a new word, but I think you see what it means, straight line motions like this. What single displacement could have taken me from the initial starting point to the very last terminal point? Well, it's obvious, isn't it? Obvious is the most dangerous word in the English language, but I think, nevertheless, that if I'm ever justified in using it, it's justified right here. That it is obvious that the single displacement that could have gotten me from here to here is the one that starts here and ends over there. Now, what have I shown? That the law of addition of vectors can be extended to 3 dimensions with no trouble at all. It's just as easy to visualize in 3 dimensions as it is in 2 dimensions. So that I can put here R, for example, equals C plus D plus E. Has been illustrated here. If I call this one C, D, and E, it doesn't matter whether I'm in 2 dimensions or in 3 dimensions. Well, I wonder if we know now what a vector is. I'll put down here what is required of a vector. A vector has the following characteristics: direction, magnitude, and, very important, a law of combination. Like displacements, let's say. These are 3 characteristics which we must look for if we are considering whether something is a vector or not. Yes?
Could you tell me what units vectors are measured in?
What is it measured in? Actually, it will turn out, the answer to your question will turn out to depend upon what kind of a vector we're talking about. If it's a displacement, it will be measured in meters, miles, feet, and so on. We will learn later on that there are other vectors like velocity, and that would be miles per hour, meters per second, or force, you see, and that might be newtons, or some other unit of force, and so on. So it depends upon what the vector actually illustrates as to how it will be measured. Let's consider now some other examples of vectors other than displacement. We can move in a natural way from displacement to velocity, and let me do that by means of the following example. I have a device here in which the weight can experience an upward displacement. It can be just lifted. But you see it's constructed in such a way that I can also give the rod on which the weight goes up a horizontal displacement. Now, when I push this board, you will observe that it will have both horizontal and vertical displacements. Now, let me put a mark here just roughly to indicate where that is. Let's say that mark indicates approximately where that was. Now, let me push this, and let's see what happens. You see, it started here and ends up here somewhere. It underwent two displacements simultaneously, one horizontal and one vertical. And I think you can sense that it was obeying the law of displacements that we were talking about, you see. The resultant would have gone off along a diagonal. But something else happened here that did not happen in this illustration. Here, this was a static illustration, nothing moved. But here, I actually had motion along with the displacement. So you sense, I think, that the velocity is also a vector, because I had velocity this way plus velocity this way equals velocity this way. Let me show another illustration that has to do with velocity. Now let me just move this over here. I want to use one of these pegs as an indicator. I've got to have this clear. I want to use this peg just as an indicator of motion or the lack of motion. Now this device can be made to move. Let me test it first. All right. Now, this is what I want to observe. Anyone who has gone down on an upgoing escalator knows what I'm going to illustrate here. I will allow this to move, but I will move the cart in the opposite direction. Now, this will be my indicator. Let's see how well I can do this. I tried to keep it right next to this. Now, in vector language, how would we say that? I have shown in a very simple case, almost trivial case here, that if you have a velocity going like this, considered as a vector, if you add it to another velocity, now that means you see that I have to tag the foot of this one to the head of the previous one, and I have V2 like that. And notice that V2 equals minus V1, although I haven't defined what minus is, but you see how naturally we can talk about it. At any rate, certainly considered as a problem in addition, V1 plus V2 is equal to 0. You see, because the resultant really goes from this foot to this head. They're actually coincident, and therefore this holds true. So, going back now to my symbols, I think I should put here, I don't really need this, a summary of the symbols that we've used so far. We have that, and we have the 0. And you might raise such questions as this. Is this going to have any meaning in our algebra? I'll leave this as a question because I'm not actually going to get to it in this hour. Will this symbol have a meaning? Will this symbol have a meaning in our algebra? Well, we've said a lot about what things are vectors. Is it possible that there are some things that are not vectors? I have two blocks here. And let me put them so that they are parallel to one another. And I'm going to consider rotation as a possible vector. For example, I can discuss direction by considering that the axis has a direction and the angle through which I turn has magnitude. So let me rotate this about a vertical axis through 90 degrees in a clockwise sense. Now let me rotate it about a horizontal axis through 90 degrees like this, and I end up with the block like that. Now this time I will start off with the horizontal rotation, rotate it through 90 degrees. And now I will rotate it about a vertical axis through 90 degrees. And they end up differently. In other words, although I had things with direction and magnitude, the direction was the axis direction, the magnitude was the number of degrees, I find that A plus B does not equal B plus A. But that was one of the requirements, you see, that C plus D equals D plus C, that we should be able to commute. All right, the moral to this little story is that it's not enough to have direction and magnitude. It has to obey the law of combination, which was peculiar to displacements. And therefore, we can't go about accepting anything that comes along as a vector simply because it has direction and magnitude. In my list of vectors so far, I put down displacement as the most obvious one. In my notes I had put it's the primordial vector, and one of the comments that I got was, what's that? Well, it's the most primitive vector. It's the one most easily recognized, or the one easiest to visualize. You see, my initial demonstration was done with displacement. Then I went over to velocity. And perhaps now you will see why acceleration is going to creep into the picture. But certainly the ones that are related to motion are the easiest vectors to consider. Now I will put here a word. Scalar is a word that has to do with things that have only magnitude but not direction. Now it is said that someone was delighted and surprised to find that he had been speaking prose all his life. He had never heard the word prose. Well, you may be delighted and surprised to know that you've been using scalars all your life, and perhaps you haven't called them that. Examples are mass, has magnitude but no direction, temperature, there is a word associated with velocity, speed. Speed is a number that you get from a speedometer, but it doesn't give you a direction. So we put speed in this category, velocity in this category, and so on. Scalars are the quantities that add according to the 2 plus 2 equals 4 kind of addition. You see, ordinary addition. Scalars obey ordinary addition. Very often, in vectors you will have 2 plus 2 does not equal 4. 2 plus 2 might equal 3, 2 plus 2 might equal 0 in a certain sense. So there's obviously an important difference between the behavior of vectors in our algebra and the behavior of scalars. There is an operation associated with scalars which is very easy to visualize. Let me show it with my rubber vectors. Suppose I call this vector A. Now I could tag onto this another vector A, and of course the result would be 2A. But obviously I could just do it this way. If this is A, this must be 2A. If this is A, let's say this is 2A. And 3A would mean a vector that has the same direction but 3 times as long. And if I try to stretch this 3 times its original length, it will pop. I know, because I tried it last night. Now suppose I consider a vector like this one and call it the vector B. If this is the vector B, what shall be the meaning of minus B? Any ideas? Yes.
The same thing going in the opposite direction?
Well, it certainly sounds reasonable enough. This turns out to be correct, and it can be reconciled with what we will say later about subtraction. It seems reasonable, you see, that if I call this vector b, then the vector that goes just opposite to it has the same magnitude but opposite direction will be called minus b. And so I come now to the concept of multiplication by a scalar. Perhaps I should add it here to my list, maybe over here. Let's say, what do I mean by k times a? Well, it's a vector that has the direction of a, but its magnitude is k times the magnitude of a. So that takes care of 2a, 3a, and minus a also. See, minus a is a special case. I can have negative scalars. So here are my operations now: addition, multiplication by a scalar, equality, and 0. My vector algebra is growing. I have one more operation that I want to discuss, and that is subtraction. Facing the wrong way. Suppose I have here two vectors, and I keep their directions and magnitude alike. Well, we've already called them equal. We've already said that they're equal vectors. Suppose I pose the question this way, though. What is the difference between these two vectors? How would we answer this? You could say 0, you could say there is no difference. All right, now, suppose then I consider this situation. Perhaps I'll do it over here. Make the magnitude of one of these a little bit longer than the other. The difference between these two vectors is a vector that goes from the head of the short one to the head of the long one. Does that seem reasonable? All right, now I want to change the direction of this one a little bit. How would you define the difference between these two vectors? Anybody got an idea? Yes?
The straight line difference between the two heads.
In other words, do exactly what we did before. Go from the head of this one, I have to wiggle it so you can see it, to the head of this one. A vector that goes from here to here seems reasonable to define as the difference between the two vectors. Now I'll put that on the board so that we can keep it here with our summary. If I have a vector like this one, I guess I can call it A. Doesn't matter that we have other diagrams there. The rule was you tie the feet together. Let me get this out of the way. And let's say this is B. The rule is that you go from here to here. And the symbol that we will associate with this will be B minus A. And now I have added one more symbol here to my algebra. Question?
How can you tell if the vector, the resultant, goes from the head of A to the head of B or the head of B to the head of A?
Let me do it by going to the blackboard and drawing this vector. I will call that B so that it will be the same notation that I use later on, and call this one A. If you have to imagine these two tied to the same point, I want to discuss the meaning of B minus A. Well, if they happen to both go in the same direction, I think it's easy to visualize that I ought to go this way and say the vector that goes, let me write down B minus A. The vector that goes from the second arrow to the first arrow. The vector that goes from the second one, the one that appears second in this statement, to the first. That will be my set of instructions. Now let's go back here to this board and see whether I follow that. I've called this B minus A. A is the second vector. I've gone from the head of the second vector to the head of the first one. So this obeys the same set of words anyway, you see? And this in general will be how we will define the difference between two vectors. I think it's easy to remember the motivation behind difference by considering this simple idea. Suppose you had two boys, and one was tall and one was short, like that. And you wanted to know the difference between their heights. Well, you see, you put their feet at a common level, then you would put a meter stick here on top of this one and find out how much taller he is than the other. The idea is you put the feet together, and then you find how to go from this head to this head. That's exactly what we're doing here. You put the feet together, you go from this head to this head. Question?
Suppose you take a larger vector from a smaller vector as b from a.
I want not b minus a, but a minus b, okay? So I'll say, what is a minus b? Question mark. All right, I'll erase this because I don't know the answer yet. Well, I'll follow the same words and say, b is the second vector. So I must go from the head of the second vector to the head of the first vector. There's the answer. So there you have it. We've defined what we mean by a vector, a quantity that has direction and magnitude and obeys a certain law. We have shown that one can invent an algebra in which symbols like plus, equals, 0, and minus have meaning. There are meanings a little bit different from the meanings that they had with ordinary algebra, because we're not comparing numbers, we're comparing new quantities called vectors. And we've also indicated that there are some practical applications.